Welcome back to the show, everyone. Today, we're diving deep into the exciting world of autonomous driving, specifically exploring a new approach that promises to make self driving cars even safer. Joining us is lead researcher Name, a brilliant researcher at Woven Planet, who's been leading the development of this groundbreaking technique. And to provide some expert context, we're also joined by field expert Name, a leading voice in the autonomous vehicle industry.
Thanks for having me. I'm excited to talk about this research, which I believe has significant potential to push the boundaries of autonomous driving safety.
Absolutely. It's a hot topic, and we're all eager to hear how this new approach tackles some of the critical challenges facing autonomous vehicles. So, let's start with the big question. What's the core idea behind this research? What problem are you trying to solve?
Well, the goal of autonomous driving is to navigate public roads safely and comfortably. To enforce safety, traditional planning approaches rely on handcrafted rules to generate trajectories. While these systems work reasonably well in controlled environments, they struggle to handle complex or unfamiliar driving scenarios. Machine learning-based systems, on the other hand, have shown tremendous promise in scaling with data and learning more complex behaviors. But often, they ignore the valuable information contained in the distributions of trajectories for both the self-driving vehicle and other road agents.
So, it's like trying to predict the future of a complex system with only a limited set of rules, right? You're essentially trying to capture the full spectrum of possibilities, not just the most likely path.
Exactly. That's where SafePathNet comes in. Our approach models the distribution of future trajectories for both the self-driving vehicle and other road agents, using a unified neural network architecture. This means we're not just predicting a single, most likely trajectory, but rather a set of potential future paths with associated probabilities.
That's fascinating. So, how does this distribution of trajectories actually help with safety? Can you explain the concept of mixture of experts in simpler terms?
Think of it like having a team of experts, each specializing in a different driving style or scenario. One expert might be cautious and prioritize smooth braking, while another might be more aggressive and focus on efficient acceleration. SafePathNet learns these different driving experts and assigns probabilities to their predictions based on the current driving situation. During inference, we select the trajectory that minimizes a cost function, taking into account both safety and the predicted probabilities.
That's a great analogy. So, you're essentially training a model to learn a diverse set of driving strategies and then using this knowledge to make informed decisions in real time. Can you elaborate on the architecture of SafePathNet? How does it actually predict these different trajectories?
Sure, the architecture is inspired by previous work in autonomous driving, specifically VectorNet and DER, which leverage the power of transformer networks. Our model receives a vectorized representation of the driving scene, including information about the self-driving vehicle, other road agents, the static map, and dynamic elements like traffic lights. This data is then encoded by a series of PointNet-like modules, which compress each input element into a single feature vector. These features are then fed into a transformer encoder-decoder network, which learns the complex relationships between all the elements in the scene. The decoder then queries the encoded features to predict a set of future trajectories for the self-driving vehicle and each road agent. We also incorporate a kinematic model to ensure that the predicted trajectories adhere to the physical constraints of the vehicle.
So, the transformer network is essentially learning how different parts of the scene interact and influence each other, allowing it to predict a range of potential futures. That's impressive. And how do you train this complex model? What's the learning objective?
We use a technique called imitation learning, where we train the model to mimic the behavior of a human expert driver. The learning objective is to minimize the distance between the predicted trajectories and the ground truth trajectories recorded from the expert driver. This way, the model learns to generate trajectories that are consistent with safe and efficient driving behavior. We also add a regularization loss to encourage smooth and predictable driving by penalizing excessive jerks and curvatures.
So, you're essentially teaching the model to drive by showing it a bunch of good examples and then rewarding it for getting closer to those examples. That makes sense. But how do you deal with the different driving styles that might be present in the data? What about the issue of mode collapse, where the model might only learn one dominant driving style?
That's where the mixture of experts approach comes in again. To avoid mode collapse and ensure that the model learns a diverse set of driving behaviors, we use a winner-takes-all approach. This means that during training, we assign a winner to each predicted trajectory based on its cost compared to the ground truth trajectory. The winner is then used to update the model parameters, effectively promoting the learning of diverse driving strategies. This is similar to what they do in the DTR object detection network, where they match predicted objects with ground truth objects.
That's very clever. It's almost like letting the model compete with itself to learn different driving styles. But what about when it comes to making decisions in real time? How do you use this distribution of predicted trajectories to choose the safest path?
That's where our inference time planning policy comes in. We have a few different policies, but the most effective one is called min-cost CC. In this policy, we first assign a cost to each predicted trajectory based on its probability, with higher probabilities corresponding to lower costs. But we don't stop there. We also perform a collision check, where we examine the most probable futures for other road agents and see if any of the predicted self-driving vehicle trajectories would lead to collisions. If a collision is detected, we penalize the corresponding trajectory by increasing its cost. This way, we prioritize trajectories that are both highly probable and collision-free.
So, you're not only considering the likelihood of a trajectory, but also its potential consequences, like a collision. That's a very proactive approach to safety. Can you tell us about the experimental evaluation of SafePathNet? What kind of results have you seen?
We evaluated SafePathNet in a couple of different ways. First, we used a realistic closed-loop simulator where we simulated the self-driving vehicle's physics and log-played the behavior of other road agents. We compared our approach to a method called SafetyNet, which uses a two-stage pipeline with a rule-based safety layer on top of an ML-based planner. Our results showed that SafePathNet achieved comparable performance in terms of estimated contacts and close calls, but with significantly fewer discomfort breaks and less passiveness. This means our model is able to drive safely without compromising comfort, which is a key factor for user acceptance.
That's impressive. So, your approach is not only safer, but also more comfortable. And you've also tested this in the real world, right?
That's right. We deployed SafePathNet on a real self-driving vehicle and conducted extensive road tests in challenging urban environments. We observed that the model was able to handle complex situations like yielding to cyclists, navigating busy intersections, and even executing cut-in maneuvers safely and smoothly. This real-world validation gives us a lot of confidence in the potential of SafePathNet.
That's amazing. But as with any new technology, there are always limitations. What are some of the challenges or limitations of SafePathNet?
Certainly. One limitation is that the predicted distribution of trajectories isn't guaranteed to contain a collision-free trajectory in all cases. However, we found that the model can learn to predict more diverse and safer trajectories by training on a larger data set. Another limitation is that, while we don't rely on an external rule-based planner, we do use a handcrafted cost function for trajectory selection. Although this cost function is designed to prioritize safety and collision avoidance, it could potentially be improved further in the future. Finally, while our closed-loop simulation results are promising, they are not fully reproducible due to the reliance on proprietary datasets and simulation tools. However, we believe that the results clearly demonstrate the benefits of our approach.
That's an important point. Transparency and reproducibility are crucial for building trust in autonomous driving systems. What are some potential future research directions that could address these limitations?
One area we're exploring is improving scene consistency, ensuring that the model's predictions are not just safe, but also consistent with the overall dynamics of the driving environment. We're also looking at developing more sophisticated cost functions, potentially incorporating more factors like efficiency and comfort into the trajectory selection process. And finally, we're working on developing more robust, real-world testing methodologies that can better account for the complexities and uncertainties of real world driving conditions.
It's clear that there's still a lot of exciting research to be done in this area. What are your thoughts on SafePathNet and its potential impact on the autonomous driving industry? This research is incredibly promising. SafePathNet addresses a critical need in the autonomous driving industry: the need for safe and reliable planning systems that can handle complex and unpredictable driving scenarios. By learning a distribution of future trajectories and incorporating collision checks, this approach has the potential to significantly improve safety and accelerate the deployment of autonomous vehicles. However, it's crucial to remember that data dependency is a key challenge for all ML based systems, and real world testing is essential for ensuring that these systems can reliably operate in diverse and unpredictable environments. We also need to consider the ethical implications of deploying autonomous vehicles and ensure that they are used in a responsible and equitable manner. Absolutely. The ethical and societal implications of autonomous driving are just as important as the technical challenges. We need to be mindful of these issues as we develop these advanced technologies. Thank you so much for sharing your insights into this cutting edge research. It's incredibly exciting to see how machine learning is being applied to solve such critical challenges in autonomous driving.
Thank you for the opportunity to share this research. We believe that SafePathNet represents a significant step forward in the pursuit of safe and reliable autonomous vehicles.
And to our listeners, stay tuned for more exciting developments in the world of autonomous driving. Until next time, drive safe.